Why we need to learn VLSI? So what is the real specialty behind VLSI design? So we have so many reasons to tell when coming into VLSI design. So let us discuss few important points like why we are selecting the VLSI course. So the recent developments when you consider in electronic systems or any kind of technological developments that all rely on a main processor called microcontroller or the DSP processor and the one of the effective processor inside the device called ASICs, application specific integrated circuits. And we are going to discuss some of the challenges that is faced by these devices and what are the solutions as of now we have in our hands, and how our VLSI design and chip design can play a major role in these kinds of developments. So when you take any kind of recent development or product, so we are seeing so many versatile options and benefits, so that these developments are made to provide easy accessibility and flexible operations. So when you take any kind of electronic devices such as high-speed modem, mobile phones, computers, tabs, and miniaturized products, the benefit which we acquire from these products are easily accessible and various kinds of options available in it. The main reason behind how we are getting various options is that we have a very versatile processor inside the device, nothing else. On the other hand, we have a high speed and customized time managing devices. So speed plays a major role in selecting any kind of devices. So FPGAs and ASIC devices are focused on working with customized speed. That means the device can adapt to lower speed as well as the higher speed. So hassle-free communication and big storage. So the device which we select in recent days based on the trouble-free solutions and big storage platform needed for us. So to store some of the images, videos, text informations, all we need is the memory. So the recent devices rely on providing higher sizes of memories. If we get more advantages on devices, obviously we have few challenges such as managing the power within that certain limit, and so many kinds of accessibility we are getting. So what about the attacks? So we may get some external attacks through the internet and third-party vendors. So is it customizable? So that is the main reason to select the device. We need customized products, which means you want to change the content at any time. It is also called as dynamic. So whether our products are dynamic, that is what we are seeing. So these are all challenges. And for these solutions, we have in recent days ASICs are integrated in the products and mixed signal FPGAs are used. High-end devices and chip developments are made to provide you a miniaturized structure of electronic product and secure and SOC protected product. So when you take the highly developed products in recent days, that we have facing so many issues in power management and area efficiency. So when it comes to ASIC, application specific integrated circuit, and various mixed signal FPGAs, we provide the solution for these kind of activities. So on the other hand, since we are more accessible in internet, SOC protected devices are highly important. So the role of chip design in these kinds of recent developments is because it is highly integrated and secure architecture is provided by the system. It is digitally controllable and less reverse engineered, which means VLSI systems are self-made, which means the designer provide the circuit algorithm with its own creativity. So various options are there to protect your circuit using the creative ideas and digital logics itself. So reverse engineering the VLSI platform is trouble, and it cannot be easily cracked by the hackers. So coming to opportunities, VLSI industry has a evergreen field. We have various opportunities in VLSI industry on chip development, You can get the positions like VLSI design engineer, RTL design engineer, front-end engineer, FPGA design engineer, RTL engineer, software engineer. These are the positions available for freshers. So let us start with a deep knowledge on VLSI design with a high level of creativity. So let us see how to get started with ModelSim software. So I open the ModelSim software here. I already created a folder. So I copy this location. Open ModelSim. First we have to create a new project. So go to File, New Project. So my existing project will be closed. So I create a new project over here. So my project name is test, and my location is where I copied the folder location, like D drive VLSI beginner course. Okay. So now it will ask for add existing file or create new file. So I'm going to create a new file, and my file name will be the test program. So where I'm going to show you various test programs over here. So we have to save using the extension called .vhd. Give OK. Close it down. Just double click it. So this is the RTL editor. So here only we have to type the VHDL codes. So apart from this, you can see various options available in the ModelSim screen. Like this window is used to compile and make the simulation of the RTL code. And you can see the view option where you can view various windows like waveform window, what we frequently use, the objects window, the data flow diagram window, and locals list, local window, everything. And if you want any other extra options, you can see the options available like tool selection, functional coverage, code coverage, source, add to wave, add to data flow, add to log, simulate, compile, everything. So now I'll show you how to create a new file and how to compile it and how to see the simulation. So let us start with declaring the library. So as you know, so VHDL start with a library called IEEE. So the basic library which we need to utilize is library use IEEE dot standard underscore logic underscore 1164 dot all, which is the standard library utilized for VHDL programming. So everything start with the entity declaration. So entity, and a basic thing is that file name and entity name should be same to avoid various problems. So I given a name called test program is, so whichever words highlighted in color or nothing but the inbuilt keywords. So for example, I start with developing a gate. So I declare a comma b as my input. So since it is a single bit, we have to declare it as standard logic. Y is my output of the gate. Then we have to end the entity. So now declare the architecture. So typing mistakes will be there. So architecture, behave of test underscore program. The entity name should be reflected here. The begin is nothing but like how we declare the open brace in C program. Begin means the process begins. So end the architecture by using end behave. So now the concurrent statement y equal to a and b. And is a keyword, so that will be reflected as red color. So now I show you how to compile and see the simulation. So click the file name, compile. You can see it is compilation successful. Compile all, simulate. So go to work folder, test program, go to OK. Now you can see a new window called objects window. Just right click it, add to wave, signals and design. So you can see A, B and Y whatever you have declared in the test program. So you can utilize A as single bit input by forcing the value, or you can give clock as input. So now I give A as per the truth table 0, 0, 0, 1, 1, 0, 1, 1. A and B I am assigning forcing to 0, 0. So now this is the run button. So now make it to B to 1, 0, 0, 0, 1. Now 1, 0, 1, 1. So this is the realization of simple AND gate using ModelSim. Apart from this, what else you can see in ModelSim software is, you can see the data flow diagram. Just click any one of the variable, click and drag it here. You can see how the software realizes the code which you have written. So double click at the center, it can be pointed to the line in the RTL program. So this is how the ModelSim software will be used. So I'll see you in the next class on how to design various combinational circuits and sequential circuits. Thank you. Simple AND gate acts as a decoder. So in VLSI design systems, in digital systems, we have combinational circuits and sequential circuits. So combinational circuits are one which depends upon the present input, whereas sequential circuit are the one where the output depends upon the present input as well as the past output. Since we started AND gate development, so how the simple AND gate acts as a decoder. So if you listen to this circuit, we have a 3-input AND gate developed over here. So this is the truth table for the AND gate. So when you want to decode a particular position from the AND gate, so particular position from the truth table, for example 101, you want to decode, other inputs should be 0. So actually this should be 0. If you want to decode any particular value, for example 101 should be high always, and next 111 should be high always. How you can able to design? I given an example for 101 alone. So if you want to make 111 to be decoded, directly you need to give 111, 101. So instead of 0, I given a NOT gate, so that the simple AND gate acts as a decoder. Only during this position the output will be 1. It is triggered as 1. So I'll show you how to write a simple code to make this circuit. So I already declared a 2-input AND gate here. So that is my test program. So I just make it to a 3-bit input. I will make it standard logic underscore vector of 2 down to 0, and Y is the output. So now I want to make the position called 101, which means my LSB should be 1 and last the MSB should be 1. In between, 1 bit should be 0. So in my code I have to write it like A of 0 and not of A of 1 and A of 2. So if I write value like this, 1, 0, 1. So when I simulate this code, you will get the pulse whenever the value goes to 101. So I simply compile. So keep practicing the compilation steps so that it will become a habit. Compile all, stimulate. So the steps are very easy. So now I got the objects window. So where A, Y will be there, go to the waveform window, right click, add to wave signals and design. So if I force value to A 0, 0, 0, so the output will be 0. So if I force any value next to 0, 0, 1, the output will be 0. So in the similar way, if it is make automated circuit, automatically will get value 0 for all the changing values. Only thing, if you give the value 101, you will get a Y output equal to 1. Unless and otherwise, whatever other inputs are coming, your output will be 0. So now a simple AND gate acts as a particular decoder. So if you want to stop a counter at this position, you can utilize this signal for making as a reset signal so that your counter will get stopped. So this is a simple logic where you can utilize a simple AND gate as a decoder. So this is the data flow diagram for simple AND gate as a decoder. Thank you. So in this session, we develop a simple oscillator circuit using VHDL program. So look at this circuit. So A is the input, Y is the output. So we have intermediate signals assigned over here with a delay. So normally each and every gate have a specific delay, internal delay present in it. So it may be 1 picosecond or 1 nanosecond, that depends upon the manufacturer. So in this circuit I given T1, T2, T3, T4 and T5 as temporary signal with a delay, and I consider each and every gate has a certain delay of 1 picosecond or 10 picosecond. So let us start programming this circuit and how a simple combinational circuit works as an oscillator. Let us see. So I already created a empty file, so where we will start typing our code. So here I declared the oscillator entity and architecture as oscillator. So I keep A as my input. So initially I keep it as standard logic only and Y as my output. So now we have a new syntax called signal assignment statement. So signal assignment statement is nothing but intermediate wires are declared as signals, which means it is neither input nor output. So that will be declared as an internal wire or internal signal. And the syntax for signal is signal, signal name, standard logic or whatever type we are using. In digital circuits only standard logic and standard logic vector will be the internal signals. So if you want to make some simulation work, so you can also utilize integers, variables, real data type and string also as a signal. So anyway it is internal purpose only. But when it comes to real time, you can utilize only signal if it is standard logic or standard logic vector. So when it comes to design, so I declare the signal. So as per the diagram, T1, T2, T3, T4 and T5 as my signal. So now I declare T1, T2, T3, T4, T5 as signal. Standard underscore logic. So now as per the design, I make the NOT gate circuit with a delay. So for example, initially my T1 will be equal to not of T5. So actually it has certain delay. So not of A. So T2 equal to not of T1. T3 equal to not of T2. T4 equal to not of T3. So T5 equal to not of T4. So now if you want to assign the T5 to Y, you can assign. So first we will check whether the closed loop is working fine. And as I said, we have to use the delay. So for making the delay, we have a new statement called after statement. So I am giving 10 picosecond delay, PS. So I assign after 10 PS to make it as a random generation. Since we want to see it as oscillation, I'll give random time periods. So if you want to see at Y, you can assign that Y equal to T5. T5 is already signal, so no need to worry about the input-output declarations. So that's all my work. So compilation is successful. Compile all, simulate. So go to the work folder, select only the oscillator. Okay. So you can see all the signals coming over. Add to your wave, signals and design. If there is no any trigger inputs, you won't get any outputs. For example, if you run, you will get only red line. So if you give any trigger inputs, like whether it is a clock, means it will be automatically triggered. So it acts as a simple oscillator. When you keenly see the variations, you can see the delays occurring over in between each and every clocks. So when it comes to design diagram, you can see the connectivities by clicking over here. T3, T4, T5, T2. You can see the variations, like that's all. So now a simple closed loop circuit for making the oscillations. Thank you. So another level of combinational circuit called multiplexer, or we call it as MUX. So today we see the design of MUX. So a MUX is nothing but a many to one operation. So this is the simple diagram of MUX. We call it as many to one operation. So M cross 1 MUX, and which has a select lines S of 0 and S of 1. So it acts as a data selector, channel selector, frequency selector based on the applications and requirements. There is no doubt in it. And practically a MUX can be realized as a LUT. LUT means lookup table. If you want to generate a new pattern or any specific pattern, you can utilize the MUX as a LUT, so that will be generated with easy configurations using FPGAs. So now shall we realize the MUX concept here. I already created a file, and I declared ABCD as my input and Y as output. So we have another input called select lines. So we call it as S as input, standard underscore logic underscore vector of 1 down to 0, because it is only 2-bit as per the diagram I have shown to you. It is only 2-bit yes. And ABCD, A may be any bits, single bit or multiple bits. I declared as 3-bit, and the concept is any one of the input will be connected to the Y based on the select lines. So 0 0 means A will be connected to Y, 0 1 B will be connected to Y, 1 0 C will be connected to Y, and 1 1 D will be connected to Y. So a MUX can be acts as a switch also. So I declared my inputs already. So now I am using a new statement called process statement. Process. My inputs are yes. Begin. Case. Yes. Is. This is the syntax for multiplexer. No change in it. y should be assigned with a when it is 0 0. In the similar way, we have to assign all the inputs. So 0 1, y will be assigned with b, and 1 0, y will be assigned with c, and no need of last option because there is a default statement called others, so that must be declared. So when other statement y equal to d, since we started the case statement, end the case statement, end case, and end the process. So we can also label the process, like when we design large circuits, we should know how to identify the process. So for easy identification, we can also name the process like mux block. So this is a user defined name only, so you can give any names. So I end the process with the label, that's all. So this is how a simple mux could be developed. So if you want to see the simulation of mux, I'll just make the simulation. Compilation successful. Compile all stimulate, work folder, select the mux. By practice, obviously you will get these steps very easily. So initially we have to assign any value to the inputs. So randomly I'll give ABCD values. And select line should be selectable by us. So right click, force 0 0. So now run it. Keenly monitor the y. 0 0, 0 1, 1 0. I'm just changing only the select option. Every time when you assign the input, we have to run. Finally 1 1. So now you can see how the y get changed. So based on the select lines, y will be assigned to either A or B or C at a time. So this is how we realize the mux. So you can see the data flow diagram, and as I said, if you give the label name, that will be reflected clearly in the data flow diagram. So that will be easier for you to identify. So keep practicing. See you in the next session. Let us start developing the next circuit, sequential circuit called latch. So as per the definition, sequential circuits depends upon the present input as well as the past outputs. So there should be some memory or the storage element in between the input and the output. Hence the sequential circuits depends upon the present input as well as the past outputs. So it consists of clock signals, so that it will be triggered using the clock and synchronized with other digital circuits. So let us design a simple latch. So this is the basic latch design. So it consists of D as an input. I given an example D latch, clock input, clear is nothing but reset, and Q bar as per the flip-flop. So the concept of D latch is nothing but the output will be latched or triggered whenever there is a clock high pulse comes over the way, otherwise it won't be triggered, that's all. When there is a clock pulse, that is the clock level is high, then the input will be triggered, else the input will not be triggered. Latches are level sensitive, which means it works at only the logical high or logical low of the clock input. So as per this design, I create the code now for your references. So I declare clock and clear as input now. So as per the design, D also input. So we can declare D also in the same line. Q and Q bar is the output. Q bar is nothing but the complement of Q. So here we are developing only the functional architecture of the system. Hence we no need to bother about the Q bar. So it is obviously the complement of Q. So I directly writing the code with Q. So I create a process and I'm naming the process as latch. Whenever there is a reset, that is the clear is been 1, then the entire latch should be goes to 0. So the previous value of Q should also be goes to the default value called 0. Any other default value also you can provide, or the previous state also can be assigned. So this is the syntax for latch. So my previous value is Q equal to 0. I'm ending the process and 2 times I'm ending the if statement. So if it is rising or falling edge of the clock, we use ELSIF instead of ELSEIF. So here we are looking for only the trigger value, that is the clock should be completely high or completely low. So I'm making it as ELSEIF clock equal to 1. I'm ending the process. So now I simulate the code and show you the output. This steps should be practiced. You have to open the waveform window, everything. Clock should be right click and give clock since we are doing only simulation. Clear should be right click, force to 1. Normally active high reset only we use. D should be forced to any value because D we only going to trigger. So slowly we can make the trigger. So I'm making clear to 0 now, then only the reset will work, the latch will work now. So it is waiting for the clock to change. So now we apply D equal to 1 so that at every time when the clock level goes to high, it wait for the D value. So whenever D goes to low or high, whatever changes happening in the D, that will be transferred to the Q only if the clock is completely high. So that's the difference we want to view here. So Q bar we not yet assigned anything, so it is coming as a red line. So here you can view whether it is triggering properly. So whenever the clock is completely high, then only you are getting the trigger value, and it wait for the next trigger to come. Until that the clock will be, that is the Q will follows the same value. So as per this diagram, so the same thing happens, only till clock high the D will be transferred to Q until the next clock comes, that will follows. So that's the simple design of latch. And coming to data flow diagram, a simple diagram you can see that looks like a latch. So that's all the RTL code for latch and realization of latch with the simulation of model cell. Thank you. Let us see the next sequential circuit design called flip-flop. So rather than latches or level sensitive, flip-flops are edge sensitive, which means the flip-flop can be triggered at the rising edge and falling edge of the clock, which is one of the important sequential circuit that can be utilized in most of the digital systems. So as per the design, so flip-flop is nothing but we have a different types of flip-flop starting from SR flip-flop, JK flip-flop, D flip-flop and T flip-flop. And D flip-flop is the commonly utilized flip-flop in all kinds of VLSI systems. Since for triggering operation to work as a flip-flop, only one input is enough to make the trigger. In SR flip-flop, we have a forbidden problem, and in JK flip-flop, we have the trigger problem at 1-1 condition. So that is nothing but toggle problem. Hence, finally, the D flip-flop with one input acts as the recommended and foremost best flip-flop for digital system. And T flip-flop, sometimes wherever you want to design a triggering circuit, we can utilize the T flip-flop. That's all. So as per the design diagram, D flip-flop is shown here. So with respect to clock, rising edge and falling edge of the clock, either rising edge or falling edge. So here I have shown to you the rising edge of the clock. Only at the rising edge of the clock, the D input will be triggered to the Q. It is almost looks equivalent to D latch, but flip-flops are really powerful comparing with latches, because flip-flop trigger only at the rising edge where very less noise impact will be there. During the level of clock, more noise impact will be there, and during the rising edge and the falling edge, the impact of noise and external sources will be very less. Hence, flip-flops are preferred comparing with latches. So, shall we design a new flip-flop with the existing circuit? I'll show to you. So, I opened an empty file. So, I just copy this syntax which we already written for latch. I'll just rename it as flip-flop, FF. So, I need to declare the architecture. I'll just copy all the latch syntax because very small changes in the flip-flop. So, I'll just copy and paste the syntax of latch, make it to flip-flop. I named the label as flip-flop. This is the code for latch, and now we are converting that code to flip-flop. So here you can see in latch, else if clock equal to 1 we have given, since it is a level. So now I am making it to ELSIF rising underscore edge. This is the syntax. Rising edge of clock. Then Q equal to D. Whenever the rising edge comes, whatever available in D, that will be transferred to Q. In VHDL for ELSIF syntax, no need of end if statement. Directly we can use the if statement for closing this if alone, that is enough. So that's all. So Q bar we didn't use. So if you want to declare Q bar, you want some complemented output, you can take. But as per the functional design, it is not required. So I just remove the Q bar. So now I am compiling the code. Compile all, simulate. Go to the work folder, select the flip-flop, give OK. Go to the waveform window. Just right click at the objects window. Add to wave signals and design. Give clock equal to right click and give clock. Clear equal to right click and force to 1 initially. Now just make a run. You have to give D, right? Here I am just giving D as a clock. I am giving a long clock like 500 is my period. So now run the clock. So now nothing is transferred to Q. Only if clear is released. Now at every rising edge of the clock, the Q will be transferred. That is, the D will be transferred to Q. So you can see the difference in D when it is a flip-flop, because it waits for the rising edge of the clock, there is a slight changes at the Q, you can see. And coming to data flow diagram, it's similar to that of latch, only thing the label will be changed. So this is the realization of flip-flop, and this is the code. This is the code for flip-flop. You can access the code and all the screens to the link which we have given. So let us design a next circuit using this flip-flop and latch. So few other sequential circuits are really important, like shift registers and sequential mux, or then LUTs, lookup tables are there. Definitely I'm going to teach that lookup table, and we'll be completing the this course with the mini project sine wave generator. Thank you. Let us see the next sequential circuit using the flip-flop circuit. We have seen it's a counter. So how to design a counter using VHDL? It's one of the important digital circuit. So without counter we cannot able to generate a pattern of clocks. We can able to decode the specific pattern, and we can count the clock as well. We can generate new clocks also. So counter is one of the important circuit. So this is a simple 4-bit counter, and I have illustrated how the counter works. So counter is nothing but which is used to count the clock. So with respect to clock and reset, so we initially give the data at every rising edge of the clock, rising or falling edge. So here I have given rising edge, 1 bit will be counted. So I given as a +1 acts as accumulator. So at every time the clock triggers at rising edge, so 1 count will be added up. That's the basic logic of counter. So I'll show you how to make a counter design. So I took a empty RTL editor. I just copy the previous template, like clock divider code I will take. So I make it as counter entity. Since the entities and all same, I just copied that. And clock clear or 1 bit, so refer this, but the data will be 4 bit. So now declare a new input called data. So input standard underscore logic underscore vector of 3 down to 0, and our as per the diagram the output will be Q or Y, whatever it may be, that will be 4 bit. So now make the Q equal to standard logic underscore vector of 3 down to 0. So since I am going to add the same kind of operation, so I need a temporary variable that also should be in 4 bit. So standard logic underscore vector of 3 down to 0. So now everything is clear, and I renamed the label as counter block so that it match with my work. Counter block, and temp equal to initially 000, from which count also you can customized count also you can make. So temp equal to temp plus 1, that's all. So one more thing you need to note at this point, like we are making the accumulation operation. So here we are newly adding the arithmetic operation, so we have to include another library called use IEEE dot standard underscore logic underscore unsigned dot all, which is opted for arithmetic operations. So we have a set of around 10 to 11 library files that will be mentioned in the document, and depends on the requirement only we will start adding up the libraries. If those libraries are not required, means we can ignore it. Okay, so I added the arithmetic operation, so I added this library, and the purpose of each and every library will be mentioned in the document. So counter, I'll run the counter code. So compile, compilation, simulate. I hope you watching the previous videos, you become familiar about how to utilize the model sim window, clock by applying clock, clear by applying clear. If it is not familiar, please go and see the previous videos and come back here, so that will be very easier for you to understand the codes. So data initially I given as 0, 0, 0. So slowly run, make the clear to release. So this clear is nothing but the completely the hardware operation, like how the switch, that is the reset switch, works. So now you got the counter output. So at the rising edge of clock, so one count will be triggered. And the beauty of digital design is, by designing one circuit, you can get another outputs. Like a simple counter acts as a clock divider also on the other hand. So you can see the clock is being divided by 2 in 0th pulse, that is the LSB, and divided by 4 in first, divided by 8, divided by 16. So similar way you can utilize a simple clock divider also used as a clock generator. So that's the simple clock divider counter circuit. Simple 4-bit counter. Let us see the next sequential circuit design using a flip-flop called divide by 2 clock divider. So divide by 2 clock, which means if you are giving a 10 MHz as your input, then you will get a 5 MHz as your output. So look at this circuit, a simple clock divider using a flip-flop I have shown here. So in this flip-flop we have a D latch. Initially I am assigning the D as manual assignment. For example, initially we are giving it as 0, then it will be passed to the flip-flop and the complement of the Q output will be assigned back to the D. So now this D acts as a signal, right? So it acts as an intermediate signal. It is neither input nor output, because there will be some continuous looping operation will be going to be happen here. Look at the timing diagram. When clear equal to 0, whenever the clock rising edges come, the Q will be triggered, that is the complemented. If it is 0, it is complemented to 1. If it is 1, it is complemented to 0. That's all. So when you design this clock divider, you will get, if you give the input as 10 MHz, your output Q generates 5 MHz. Divide by 2 clock divider. So this is the truth table. So let us have a look at this small design, a simple clock divider using flip-flop. So I take the empty code RTL editor here. So I just take the syntax of complete flip-flop which we already written. I copy and paste the code and I rename the flip-flop into clock divider. So initial stages, these kind of VHDL coding will be tougher, but VHDL acts as one of the robust programming language. So once you start coding, it will become easier. So label the things properly. Divider. So I am naming my block as clock divider, process as clock divider. And as per the given diagram, Q will be knotted and given to D. So which means here we have to make a small change, that intermediate signal should be there, right? Because we can't read the output port. Hence, two things I can do. One, I can declare a new signal, maybe I can name it as temp, standard underscore logic. So I will work with the temp, then I'll assign the value to Q. So temp equal to not of D, but initially we didn't assign D equal to 0. So if you are assigning D equal to 0, that should be here. So now output will be not of D, and now the D value should be temp. Then only it will continuously triggers, and the clock will be rising edge of the clock and behave similar operation, no changes. Now I am running the code for you. I got one error. One error. Cannot drive the input signal mode. Yes, we can't assign it to the input, right? So now I have to make the D as a temporary variable, unless and otherwise if we are making it as not of D and assigning the same to D equal to temp, which means it's similar meaning as this one, right? Temp equal to not of temp, because as per the design I am just naming the temporary line as temp equal to not of temp. So this is a closed loop we are going to create. So exactly temp equal to not of temp will be matching. And finally I assign the value to Q. So now it will be working. So D no need to assign because it is a input. And in this case here instead of temp we can assign D, so that D will be utilized. So guys, work out with this code. So during workout only you will get lots of doubts and errors. So you can contact us anytime for any kind of doubts. Clock clear equal to force to 1. So initially as per the diagram I am just making it to 0. So here in this diagram I shown no, initially D equal to 0. I am making initial value should be 0. So assign to 0. Now slowly run it. Release the clear. This step you should not forget. Unless you didn't clear, release the clear, you won't get the output. Okay, now this clock is being divided by 2. So if you are giving 10 MHz, your output will be 5 MHz. 5 MHz means time period will be increased, frequency will be decreased. So when coming to timing data flow diagram, you can see the output like this. Everything looks like a register because it is a RTL, register transfer logic. So we'll see the next sequential circuit. Let us see the next sequential circuit called shift register. So shift register is a combination of various registers flip-flop which we already saw in our previous circuits. So shift register is one of the important element in digital systems design. So the circuit for a sequential shift register you can understand using a D latch. So the functional definition is that every clock pulse, the rising edge of the clock pulse, one bit will be shifted to the next register. So it can shift one bit at a time and triggers at every rising or falling edge of the clock. So a simple shift register acts as a pattern generator for specific inputs also. So depends upon the requirement, the shift register plays its role. And practically the shift register also utilized in pseudo random number generator that will be act as a vital role in satellite communications. So pseudo random generator, if you don't know what is pseudo random generator, visit the definition link there. And pseudo random generator is a repeated random generator. Pseudo means repeated, random number means undetermined number. So repeated random number generator is called pseudo random number generator, that will be derived from the shift register. So shift register is It's a basic circuit that will be helpful for various applications in digital systems. So shall we design the simple shift register using the existing code which we saw in the previous section. So I take the code which we have developed as a 4-bit counter for our references. So I open the shift register empty file. So I rename the shift register name. So as per like how we done the previous codes. So I saved it. So now my data is same, 4-bit I am loading as input. And another specialty of shift register is we have a third input called load, because when we want to load the data into the register, so clock will be given, clear will be given, but we have a extra input called load. So when we have to apply the value into the circuit, so a new value want to fetch into the shift register, at that time this load will be utilized. Hence there is a changes in our process statement. So first rename the process statement like shift register. So I just rename it as SR block shift register block. So if clear equal to 1, temp equal to 0 initially, no change in it. Rising edge of the clock, if load equal to 1, then the temp value will be varied. So the temp value will be D, that is D means data, data, whatever new data that will be given. Only at the else condition the shift register works. So for easy understanding, I am just shifting 1 bit at a time. So as I know, as per the theory, we have 4 types of shift registers: serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. So now we are giving the data parallelly. Complete data will be fetched inside and shifting the data out serially as well as parallelly. So now simply telling my temp of 0, and in the shift register we have an option called a fetch by 0, fetch by 1, which means what is the last value fetched inside the shift register. So temp of 1 equal to temp of 0. Slowly we are shifting. Temp of 2 equal to temp of 1 now, and temp of 3 equal to temp of 2. So 0 to 3 only. And now what is temp of 0 means we have to fetch it by 0 or 1. So if you want to make fetch by 0, temp of 0 less than equal to 0. So this will make the last value temp of 3 out to 1 bit, like say example y equal to temp of 3, and 1 bit output we have to declare, we not yet declared. So I declare y as output standard underscore logics 1 bit out. So here I have designed serial in, parallel in, parallel out as well as serial out, both the shift register inside a single logic. So I have to end this using endif, and again for this I have to declare another endif. And Q is 4 bit, so Q equal to temp, this is correct. So now I run the shift register. I have some errors. Let us clear the errors. Line number 24 saying illegal target, I'm sorry. So single quote I have to mention. That's all. So shift register. So hopefully this will be the last element in digital design. So far we have seen gates, flip-flops. So now give clock equal to 0. Clear clock equal to clock. Clear initially it should be 1. And load should be generated with the pattern called 0, and data I'll just give us a default data value 1100. So now run it. We not yet shifted, so shift register not yet started to shift. Now make clear to 0. Now the shift register is ready to shift, so the Y becomes 0 but not yet shifted. So now you make the load equal to a pulse, a small pulse, so that the input will be loaded. Now the input is loaded inside. Now make the load to 0. So always the load should be a single pulse in the initial stage. That's all. So now the input will be shifted 2-3 times. That's all. So this is a right shift operation we have done here. So even you can see the single bit coming over here as an output. So verification of data flow diagram is quite interesting. So this line refers to the value here. So that's all about shift register. So far we have seen shift register, AND gate, OR gate, XOR gate. So initial gate coding we have done, and simple decoder, oscillator circuit, multiplexer, decoder, latches, flip-flops, clock divider, counter, and shift register now. So almost around 9 elements we have seen. So these elements are really helpful to generate any kind of digital circuit. And as the end of this basic training session, so we'll be ended up with a small mini project design using the shift registers and LUT, sequential LUT I'm going to show you with the sine wave generator. So there is a term called numerically controlled oscillator. So how to make our FPGA as numerically controlled oscillator, that we are going to see here. So let us see how to design a simple mini project in VHDL. Like I given a sine wave generator with NCO. NCO is nothing but numerically controlled oscillator. So when we want a digital system with a specific kind of pattern generation is required, we have a pattern in our hand in the form of integers. So we can utilize the NCO, that is numerically controlled oscillator concept, using a LUT in VHDL. So here I am going to generate a sine wave with the concept of NCO, and the main core element which I am using here is the mux. So the mux will be converted into lookup table. So I am showing you how to make this implementation. So we have a mux here. So this is the sine wave. I am just showing as a simple sine wave, started from 0 to 0 crossing, and 1, 2, 3, the same thing will be repeated. So this is the numerical pattern I want to generate. So if I want to realize my FPGA as a sine wave generator, I have to load these values inside the memory of the FPGA using a LUT mux. So here I am going to design a simple 4-bit counter, so that 4-bit values will be continuously varied with respect to the clock, and those 4-bit will be given as a select input to the mux. So if there is a 4 select lines, means 2 power 4 combination output will be generated. That is 16 outputs will be generated. Here we have only 13 inputs approximately. So we have to adjust the sine wave according to it. So this is a sine wave I mentioned as a discrete samples. So I give 4-bit counter already, which we have developed the 3-bit counter. The same code I will take and make it as a 4-bit counter. Then I will automate the mux. Mux is a combinational circuit. I am connecting the combinational circuit with the sequential circuit. So now my mux has become sequential mux. And since we are loading the values, lookup table, looking up of certain pattern of values into the mux, now my mux acts as a lookup table. So let us see how to design this circuit effectively to have a simple mini project in VHDL. So our base circuit is counter, so we can directly take the counter coding here, so that will be easier for us with less number of typing. So VHDL is a robust programming language, but definitely have a large typing work. So I rename it as sine wave underscore gen. You can see my entity name and file name is always same. I don't know whether you are watching this accurately. So always I am following the rules. So clock clear, as per the diagram, clock clear and data will be the input, and that will be given as a selective mux, select line for the mux. So now I am making sine wave generation. So clock clear, data will be given, and output should be actually the sine wave. Now here we will take the integer as output. So no need of Q and all. So our goal is to generate a sine wave. So I name as wave out, that is output integer. Only in simulation we can see the integer values. So other than that, in hardware or real-time output, as I said in my first class itself, only standard logic and standard logic vector, that is the digital outputs, will be generated. Even in the mixed signal processes, the input as given as analog, output will be in digital. So I declare signal. So this I take it as select line. So I just name it as SEL. So 4-bit will be given to the select line SEL. So now we have to write two codes. First block is the counter block. So that is the 4-bit counter which is already there. So for this temp we have to declare and just give select SEL. Since we are generating only the select line, directly we can import the select line. So if you want to give any specific data, means obviously you need to mention the specific data over here. Otherwise default is 0, 0, 0. And now we have to create a secondary process called LUT process. What is my sensitive part of LUT is select line, and I have a clock, and I have a clear. So begin. So initially if clear equal to 1, then my mux should goes to 0, which means my wave out should be goes to 0. So wave underscore out, the same, equal to 0. Why I am giving 0 not with the quote is it is integer. Then here I have to write the sequential mux statement. So else if rising underscore edge of clock, then now write the case statement of mux. So to remember the mux concept, I will go to the mux code. So hope you remember the mux concept. Only the case statement you have to write. So I am typing the things completely for you. So when 4-bit, no, 0, 0, 0, 0, 16 value should be there, but still we are repeating few things. So you no need to make 16-bit also sometimes, but here linearly only I am adding up. So my wave underscore out equal to, just follow the diagram. When it is 0, 0, 0, my first value will be connected to the mux output, which is nothing but the wave output will be 0. So to reduce the typing work, I just copy pasting it. Zero, 0, 1. Check the diagram. First value is 1. Then 2, 3. Likewise, we have to add 0, 0, 1, 0, integer will be 2. 0, 0, 1, 1, it will be 3, which is the highest peak. I'm just copy pasting. I'm not doing it fast. 0, 0, 1, 1, and 0, 1, 0, 0, 4, making it as 2 again, and 1, 0, 1, 1, 1, 1, 0, 0 again, and 1, 1, 1, making it to minus 1, correct? So as per this diagram, after this 0, it is minus 1, minus 2. So we are just creating a sine wave generator. So we only generating the pattern. So don't bother about how the sine wave looks. If you're looking for the exact sine wave, then you have to match the pattern accurately. So if you worry about the pattern, then you can go ahead with the values, that is the discrete values which you are getting. So just I'm typing it in only the linear format, nothing new. Minus 1. Again it should be continued. Hope you can understand. Again 0. So final value I just make it as when others condition. Others means default. So remember the MUX code. When others condition is default. So when there is any others condition, just make it to 0. Hope that will be enough. And I have to end the case first. End case. And what and all I have opened? I opened if statement. So just end the if. And I need to end the process. So now my process is LUT. Unknown identifier temp. So yes, temp I changed as select, no? Okay. Now everything is clear. Compile all select. Sine wave generator. Go to the waveform. Add to wave signals and design. You can see the wave out is coming as integer. So it's showing the minimum and maximum value. So clock, as usual, right click and give clock. So clear, right click and force it to 1. Data, if you're having any specific data, mention it. Otherwise 0, 0 will be the default. So now slowly you can run. Make the clear to 0. So now you can see the values coming over as LUT, sequential LUT. Since we are not used the 16-bit completely, so you can see the values in between or default 0. So this is the final output, and I hope you wish to see the waveform in analog format. So if you want to see the waveform in analog format, double click, format, analog interpolated, make the maximum value to 4 and give it to apply, give OK. You want to see some colors, double click, go to colors, select any color which you like, apply, give OK. So if you give full run completely, here you can see the timer will be running. So right click and zoom full, complete sine wave generation will be generated. You can see how the numerically controlled oscillator will generate the sine wave kind of thing using a simple LUT operation. So this you can utilize as a simple mini project. And yes, you want to see the data flow diagram, right? So just click and drag it here. So you can see how we integrated. Everything will be clear in the architecture. So select line is connected to this as per the diagram. So select line is connected to the sequential mux. So this is LUT. Select line is connected and waveform output is coming over here. So lot of things are there in digital system design. So this course acts as a basic informative system on VHDL programming and followed by simulations using Menta graphics tool called ModelSim. The same will be continued with other implementation tools like Xilinx ISE, Lattice, Diamond and Actel based tools also. And the final code will be dumped inside the FPGA hardware, and we also have sessions related to this hardware dumping procedure, FPGA dumping procedure that will be follows. So keep on supporting us. So that course will be given to you in the next sessions. Thank you.